Good afternoon. Am I audible? Am I audible? Is the screen visible? We will wait for others to join. We will start in few minutes. Okay, we will start the session. Good afternoon, everyone. I hope the presentation slide is visible. Welcome to the live session 5 for the course Basic Environmental Engineering and Pollution Abatement. This is Mahalakshmi S, Research Scholar from NIT-Trichy. So this is the general information. This live session for the course Basic Environmental Engineering, Pollution and Abatement will be happening every Saturday from 3 p.m. to 5 p.m. And you can join this class by using the same Gmeet link. You can note down this MDI VDCP NCG. And all these live session videos will be uploaded on the YouTube channel named Mahalakshmi S. We can find it through at Mahalakshmi Shekhar NATT. And in our today's class, we will discuss the assignment 4 solutions, and we will see the brief overview of this week 5 lectures, and we will see some sample assignment questions for assignment 5, and then we will solve the problems of this week content. Okay. Can you please confirm whether I'm audible?
Yes, ma'am.
Okay, thank you. So first we will discuss the assignment 4 solutions. The first question is, which of the following technique is or used for the collection of particulate matter? Find the most suitable option. We know that particulate matter is one of the major component of the air pollutants, right? All these particulate matter are collected by different techniques, and they are asking which of the following techniques are used. Is it sedimentation, tape sampler, impingement, or all of these? The right answer is all of these. We know what is sedimentation. So based upon the size, depending upon the gravity, the particles will get separated. And then in the tape sampler, we have already discussed, like the rolling tapes are used for collecting the uh, air dust particles. Next, the impingement method is a method which is based on the collision of particle against the sturdy surface. When the particle is getting collided, then finally these gaseous particulate matter will be getting collected in the medium. So now all these three different methods are used for the collection of particulate matter. So the right answer is all of these.
Ma'am, screen is not visible.
Is it visible now?
No, ma'am.
No. Is it not visible to anyone? Uh, can you see the slides moving?
No, ma'am.
No. Can anyone else also confirm whether it is visible or not? Yes. So S for visible or not visible? Can you please confirm? Is the slide visible? Introduction slide, general information, assignment for solutions. Yes. Okay. Uh, presentation is visible. Please check Kavita. Okay. The second question is, all of these dash involves the physical dissolving of the pollutant in liquid. In these, what are the methods which is involving the physical dissolving of the pollutant in liquid? Okay. So the right answer is physical absorption. So we obviously know that dissolving of pollutant in a liquid means itself indicating that this process is coming under absorption. And only thing you have to find is whether it is physical or chemical absorption. Since they are mentioning it as physically dissolving it, so the right answer is the physical absorption. So next question is Brinkless method is used for the measurement of what? Whether it is a COD or DO or POC or BOD. Yes, DO. So DO is the dissolved oxygen present in the water. Okay. Why dissolved oxygen is very important? We have discussed this in the last class. Because in any water system, a river water system, depending upon the concentration of the dissolved oxygen only, the quality of the water is determined. So this is the critical point below which when DO goes, no living organism can live in that type of water. So DO concentration should be achieved in the saturation percentage always. So one of the best method to estimate this DO concentration is the ring plus method. Next question is particle size analysis can be done by dash. So what is the suitable option they are asking? The right answer is the sieve analysis and the probe. Based upon the size of the particles, these particles are getting separated in both of these methods. And next question is identify the primary use of the equipment shown in the following figure for measuring dash. So this is the figure. If you see the field is going in and then the particles that were too large in size are coming out here and the separated particle in each section 1, 2, 3, all these are getting collected in the water. Okay. So this method is particle size distribution. Based upon the size of the particle passing through the predetermined mesh, these particles are getting separated. And next question is the ultimate analysis stands for the measurement of the concentration of dash in the sample. What are the component measured? Which concentration are all measured in the ultimate analysis they are asking? This ultimate analysis is also called as the elemental analysis. So this is usually measured with the help of an instrument called CHNSO analyzer. So in this one, the most suitable option is CHNO, carbon, hydrogen, nitrogen, and oxygen. So in this one, CHNS is measured and oxygen is indirectly measured by subtracting the known concentrations. Next question is match the following with their roles. Match the following organization with their roles. So the first one is the IPCC, which is Intergovernmental Panel for the Climate Change. Second one is EPA, which is Environmental Protection Agency. And next one is UNEP, which is United Nations Environmental Program. So the right answer is IPCC role is to provide the policymakers with regular scientific assessment on climate change, its implication, and the futures. So it is totally related to the climate change. Okay. Next one is EPA. So EPA, its responsibility is to create the standards and laws promoting the health of the individual persons or as well as the environment. So it is going to create the standards and laws to protect the environment as well as the individuals. Next one is the UNEP. Its role is to catalyze and encourage the international as well as the national action for more effective management of the environment. So it is going to catalyze and encourage both the international and national actions. So the right answer is 1, 2, 3. And here comes a problem. To determine the water equivalent of a bomb calorimeter, 1.1651 gram of a benzoic acid sample having the heating value of 6,318 calories per gram was used. The experiment produced a net corrected temperature rise of 3.077 degrees Celsius, and the acid titration required is 11.9 ml of standard alkali and 8 centimeter of par 45C10 nickel chromium fuse wire was consumed in the firing. Determine the water equivalent of the bomb calorimeter. So the question is equal to question is to find the water equivalent of the bomb calorimeter. So four options are given. The right answer is 2402.1 calorie per degree Celsius. We see this. So first of all, a bomb calorimeter is an instrument. So into which the sample holder will be there. This sample holder will be containing our sample. So here in this question, it is mentioned that the sample used is the benzoic acid. Okay, and the heating value of the sample is given, and the weight of the sample is also given. So what happens here is always these samples are connected to the instrument through the ignition wire. So the ignition wire here used is the par nickel chromium fuse wire. Okay, and the length of this wire ignited during the firing of the sample is 8 centimeter. So surrounding this sample, so outside the bomb, water will be there. So what happens? The heat energy liberated from the sample will be taken up by this water. So there will be a rise in the temperature of the water. So this temperature rise is given as 3.077 degrees Celsius. So to determine this one, we should be using this formula, which is W water equivalent is equal to H into M plus E1 plus E2 plus E3 whole divided by T. So H is the heating value, which is given here as 6,380 calories per gram. And M is the mass of the sample used in this analysis. So mass is 1.1651 gram. And E1, E2, E3 are the parameters used for correction. How we will determine E1, E2, E3 is it is using the formula. First is E1. It is going to use the acid titration. It is depending upon the H2SO. So 11.9 ml is used for the acid titration by using the 11.9 ml of standard alcohol. We always multiply this volume of the titrant used into 1 calorie per ml and we will arrive at the E1. So E2 is calculated whenever there is the information on sulfur is given. So in this question, no information about the sulfur is given. So we can take this E2, take out the E2 from this formula. Next is E3. So E3 is calculated based upon the type of wire used. So here the type of wire used is the nickel chromium fuse wire. So the correction factor should be multiplied with 2.3. 2.3 into the length of the wire used, which is 8 centimeter. So 2.3 into 8 is 18.4 calories, and we have to substitute all these values in this formula. So W is equal to H into M, where 6,318 is multiplied with 1.1651, then plus E1 is 11.9, E2 is not there, E3 is 18.4, whole divided by the temperature rise. So the temperature rise is 3.077. So you will arrive at the value 2402.1 calories per degree Celsius. So the answer is 2402. And next question is related to the proximate analysis. So in this one, it is the question is 1 gram of MSW sample. So they have taken a municipal solid waste sample of which the weight is 1 gram, which is heated at 105 degrees Celsius. So initial mass of the sample is 1 gram and it is heated at 105 degrees Celsius. So at this temperature, what happens? All the moisture will get evaporated. So this 1 gram sample is heated and finally after 24 hours, the weight obtained is 0.85 gram. So 0.85 gram is the residual weight. Then again what they are doing, just further heated in a furnace at 950 degrees Celsius. So again, this sample is heated at 950 degrees Celsius. So at this temperature, what happens is all the volatile matter content will get removed from the sample. And the weight loss is found to be found as 0.25. So 0.25 is the weight loss. So the right answer is 0.60. Remaining is 0.60. The weight loss is given as 0.25. Okay. And here the weight loss is 0.15. 1 minus 1 minus 0.5 is 0.15. Okay. Next, again, this 0.6 gram sample is further treated. When the temperature reaches to the ambient temperature, its lid is open and it's further heated in the oven. Again, it is heated in the oven at 750 degrees Celsius. Okay, for half an hour in the presence of oxygen. After cooling the material, the residual mass of the material is found to be. So the final weight obtained is 0.1 gram. Okay, 0.10 gram. Determine the moisture content, volatile matter, ash, and fixed carbon. So you should note down this sequence. Like initial sample weight is 1 gram, and after heating the sample at 105 degrees Celsius, after evaporation of the moisture, the weight is 0.85 gram. So 1 minus 0.85 is 0.15. So 0.15 into 100 is the amount of moisture. So which is 15%. Okay. Then the weight loss is found to be 0.25 gram after heating the sample at 950 degrees Celsius. So this 0.25 into 100 is 25%, which is the amount of volatile matter. Finally, after heating the sample in the presence of oxygen, all these will be converted into ash, and the residual mass of the material is found to be 0.1 gram. So this is the content of the ash. So 0.1 into 100 is 10%. Always the fixed carbon FC is obtained by subtracting all the percentages from 100. So here 100 minus 15, which is the percentage of moisture, and 25, which is the percentage of volatile matter, plus 10%, which is the ash content. So you have to add everything, which is 40. 40 plus 10 is 50. So 100 minus 50 is 50, which is the percentage of fixed carbon present in your sample. So the right answer is 2. Moisture 15%, volatile matter 25%, fixed carbon 50%, and ash content 10%. This is how you have to calculate the moisture, VM, FC, and ash content in any problem. So the next question is, which of the following is the correct formula for total solids? So coming to the parameters of the water sample, one of the major parameters is the total solids. We know that the total solids are classified into different types as the total suspended solids and total volatile solids and then total dissolved solids. So the total solid is further divided into many types, and it is basically estimated directly just by pouring some amount of sample in a container. So initially what we will measure is the weight of the container along with the sample. Then after evaporation at 105 degrees Celsius, until the constant dry weight is obtained, we will again measure the weight of the dish with the dried sample. Okay. Uh, what is the right formula to calculate the total solid? It is total solid is equal to A minus B divided by sample volume into 1000. So here A is the dry weight of the dried residue plus the dish. This is the container. Okay, and B is the weight of the dish. So you have to subtract these things to arrive at the weight of the dried residue, which is the weight of the solid content present in the sample. and it is divided by the sample volume. Okay, this is the right formula to calculate the total solids in the water. So now we have discussed the solutions of assignment 4. Do you have any doubts before going to week 5? Yes, I have received some answers. Any doubts in assignment 4 solutions? Okay, we will move on to week 5 lecture content. So this week 5 lecture deals about the air pollution control. We have already seen what are the major air pollutants, how they are being characterized, all these things. Now in this lecture, we will see how they are all controlled by various methods, how we are measuring them, all these things. In the lecture 21, the major typical air pollutants are discussed. We have already seen enough of this, so I will just brief about it. So one is the particulate matter, which is PM10 and PM2. Based on their size, they are classified. And next air pollutant is the ozone and NOx, nitrogen dioxide, carbon monoxide, sulfur dioxide, lead, carbon dioxide, and methane, chlorofluorocarbon, and volatile organic compounds. So these are the typical air pollutants. Okay, so these are the major processes and the equipments used for the removal of the unwanted elements from the gas. One is the particulates, and the second is the gas molecules. And when these particulates and gas molecules are combinedly present, how they are all measured. So the particulate matter are mainly collected through gravity settlers, ESP, filters or fabric filters, and cyclones. These gas molecules are collected through the wet process by the process of absorption, or through the dry process by the process of adsorption. And these particulates and gas molecules together can be removed with the help of the wet scrubbers. So this lecture speaks about the gravity settlers, and this is the basic working diagram of the gravity settlers. So in this one, we are seeing about the air pollution control. So our pollutant form is gas. Okay. So when the gas is flowing inside this gravity settling chamber, so this is the settling chamber. What happens here is based upon the inertial force and impaction over here. These particles are based upon their size or getting collected into the dust collectors. So this is a very simple mechanism based upon the gravity only the settling of the particles are occurring. Okay, and the efficiency is comparatively less here. So what they have designed is the Howard settling chamber. So here they are dividing the settling chamber into many trays. So you can see here is a tray 1, 2, 3, 4, 5. Why to partition these trays means the contact time between the uh, bottom of the settling chamber and the gaseous component is very higher here. So they are reducing the contact time so that the settling will happen very quicker, and higher efficiency will be here. When this height is divided into small sections by inserting many trays in the settling chamber. So this is called as the Howard settling chamber, and this weight fraction collected is again reported like this. Based upon the size of the particle, it is classified as less than 5, 5 to 10 micron, 10 to 15 micron, and greater than 17 micron. So here the weight per 100 gram of dust is reported in this table, and the fractional efficiency, the efficiency of each fraction from each dust size particle, how much amount is going into the filter and how much is getting collected. Based on that, the fractional efficiency, eta I percentage is calculated. So this is a model problem. The total efficiency is calculated using this formula, which is eta T is equal to summation of I equal to 1 to n mi into eta I divided by capital M. So here this mi and the capital M corresponds to the mass of the individual particle, and this m is the overall weight of the particle. Okay, so this is simply termed as the mass fraction or weight fraction, which is omega I. And eta I is the fractional efficiency, which is already recorded in the given question itself. Okay, so here to calculate the total efficiency of this gravity settling, what you have to do is calculate the weight fraction first, and you are going to multiply it with the individual fractional efficiency. How to calculate this weight fraction means, so here the total weight, the weight is given, weight fraction is given for the whole 100 gram of the dust. So this is 2 out of 100, and 10 to 15 micron particles are 4 out of 100, and 50 to 60 micron particles, or this is 20 out of 100. So this is called the weight fraction. So in this way it is calculated as 0.02, which is nothing but 2 out of 100. So 2 divided by 100 is 0.02 into its individual fractional efficiency is given as 1. So you have to multiply this. Like this, you have to multiply for all the dust size particles, and you have to add them. Then we will obtain the total efficiency of this method. So this is a model problem. We will see a problem again of this type later. So the previous lecture was about the gravity settlers, and lecture 22 is about the ESP, which is electrostatic precipitator, and the bag filter or fabric filter. So this is the working diagram of the electrostatic precipitator. This is a highly efficient one. You can see that in this electrostatic precipitator, the gas with particulates are going inside in this way, and when these gas molecules with the particulate matter are coming out, they are free of particulate matter. How these particulate matter are removed from the gas molecules means mainly by using the electrostatic forces. That is the basic principle of this method. So here there is a thin metal rod. So if you see, this blue one is the thin metal rod, and electric current is going around inside. So these particles are getting ionized, and these charged particles will be attracted to the metal plates whenever they are crossing through this plate. So the negatively charged particulates are attracted to the positively charged metal plate. So each metal plate will be having a collection plate at the bottom. When these are vibrated, these particles will move up and get collected in these plate later. So after getting collected in the metal plate, the clean gas is going outside. So to calculate the efficiency of this ESP, like how the efficiency of the gravity settlers are calculated using this formula. The efficiency of ESP is calculated by using these formulas. We can note it down. We have many problems using these formulas. So eta efficiency is equal to 1 minus e power minus ppm into AC divided by Q, where ppm is the drift velocity of the gas molecules, and AC is the collector surface area. So here is the collecting area, dust collecting chamber. So what is the area of that collector? And Q is the volumetric flow rate of the gaseous particles. Okay, and these can also be obtained by rewriting the formula as eta is equal to 1 minus e power minus ppm into AC divided by Q is rewritten as L divided by V into capital V, where the small v is the gas velocity, and capital V is the volume of the precipitator, and capital L is the length of the precipitator. Using this relation, Q into L divided by small v is equal to capital V, this efficiency formula can be rewritten. Depending upon the data, we can use either of these formulas. Next method is using the fabric filter. So this is the most efficient one with efficiency of 99.9%, and it is applicable only for the particles of size greater than 0.01 to 1 micron. So if you see this fabric filter, so in this one, the dirty gas is entering in this way and they are passing through each filter. So we are having different filters here. Filter bags are present vertically here in this chamber. So the gases are flowing through each bags and finally the clean gas is coming out from them. So the fabric cloth is of many types and the aspect ratio should be maintained and depending upon the type of dust present in the gas also these fabric cloth should be changed. So this is the most efficient method to clean the air. And in the next lecture, lecture 23, it is about the cyclone separator. So this cyclone separator, the main thing is a high-speed rotating air, that is a rotating airflow is established within a cylindrical or conical container called a cyclone. So this is the cyclone one. For the separation of particles, the only thing is the So the only thing is for the separation of the particles. To use this method, the basic principle is the particle radius should be equal to or more than zero point 0.2 times of the DO. DO is the diameter of the top outlet. So this is the outlet of the gas. So this is the inlet duct of the gas. So once the gas enters here, it will be moving around like this. So this will create the outer vortex and again after reaching the bottom, it will be coming up like this. So this is the gaseous outlet. So DO here mentioned is the diameter of the top outlet. So the particles being separated must be equal to 0.2 times of this DO or it can be more than 0.2 times of DO to get separated in this type of cyclone separator. And this is a very easy method, easy to clean and easy to maintain and it is less expensive also. Only based upon the configuration, the ratio of the height and the diameter of the outlet, what is the ratio aspect of the cone. Based on these design only, the efficiency of separation is there. Now we have seen different equipments for the gaseous pollutant separation, mainly the particulate matter. The first one is the gravity settler. It has the least removal efficiency, which is 50%, and it is suitable only for the particles of size greater than 50 micron. Okay. And one important thing to be noted is it requires a large space to maintain this instrument and the low pressure loss will also happen. And next is the ESP, electrostatic precipitator. It can separate the particles of size greater than 1 micron and the efficiency is 98%. But one of the disadvantages is high initial cost is required and it is sensitive to the variable dust loading of the flow rate. These are the major influencing factors affecting the efficiency of separation in ESP. Next is the fabric filter, which separate the particles of size greater than 0.01 micron, and the efficiency is very higher, which is greater than 99%. And these filters are susceptible to the chemical attack. So this is one of the major drawback of this instrument. Next is a cyclone separator. It can separate the larger particles greater than 5 microns, and its efficiency is also comparatively higher, which is 90%, and it is very inexpensive and less maintenance is required. Okay. So the next lecture is about the equipments used for collecting both the particulate and removal of both the particulate matter and the gaseous molecules. So the equipment used is the scrubbers. So in these scrubbers, it is only to provide the contact between the scrubbing liquid and the particulate matter to be removed. So liquid commonly used is the water to remove these matters. Okay. And these wet scrubbers are further classified as the spray scrubber, packed bed, and plate scrubber, bench scrubbers. All these diagrams are here. We will see one by one. So the first one, this is the spray scrubber. As the name indicate the scrubbing liquid here is the water. these water are getting sprayed here. So what happens here is the dirty gas will go inside like this, and it will come into contact with the sprayed water molecules. So whenever these gas molecules are in contact with the scrubbing liquid, all these dirt matters will be collected as a slurry, and it is removed from the bottom. And the clean gas alone will flow out from this wet scrubber. This is the spray scrubber. And next one is the packed bed scrubber. So here, as the name indicates, here is the packed bed. So the packed bed will be having some materials, so which is going to interact with our uh, dust particles. So whenever the dirty gas is entering here and it is coming in contact with the packed bed, it has to flow through this packed bed, and we are again introducing the scrubbing liquid from the top, and the gas is introduced from the bottom. Okay, so they are in direct contact with each other when this gas is moving through this packed bed. Based upon the size of the packing of the bed, the efficiency will also get increased in this packed bed. So again, the dust particles are collected here as slurry, and the slurry is collected from the bottom, and the clean gas will go out from the top. And the plate scrubber is a small modification of this one, where we will be using the plate column. So plates will be here, and gas will be passed from the bottom, and the liquid is passed from the top. Again, they will come into contact, and the clean gas will be present here. In the plates, what happens is the dirt particles will get settled down. From the plates, we can remove the slurries. Next method is the Venturi scrubbers. So this is based on the Venturi meter effect. So we have the Venturi type scrubber here. So the main principle is the liquid is injected in the throat section, okay, and then the dirty gas is passed from the top. Based upon its velocity, it is entering here and causing the cyclone. All the slurry particles will be collected from the bottom. The dust matters will get settled down, and again the clean gas will be passing out of the equipment from the top. Okay, this is all these are based on the contact between the scrubbing liquid and the particulate matter to be removed. Once these particulate matter are collected from the gaseous components as slurry, the clean gas is collected out of the scrubber. Okay, this is the main principle behind this wet scrubbers. And next is the gas molecules removal. These gas molecules can be removed either by the absorption or by the adsorption method. So absorption is mainly happening in the liquids, right? Through physical or chemical interaction, absorption will happen. And adsorption methods uses the solids. So over the solid, these dust particles will be present. They are just absorbing over the solid particles. These solid particles can be a silica gel or activated carbon or the molecular sieves. These can be used in this method. Okay. Next is the control of specific gaseous component. Major gaseous air pollutants are the SOx, NOx, and the carbon dioxide. The SOx can be removed by the wet scrubbing by using any of these methods. And the dry method include using the metal oxides and using the activated carbon. When activated carbon is used for this SO2 removal, this method is called rain-left method. Okay. Next is the NOx removal. So to remove, first of all, to control the NOx emissions, we have to control the parameters of the combustion. For that, they are suggesting the low excess air combustion process using the less amount of air, so that less amount of nitrogen will be reacting with the oxygen, and it will less amount of NOx will be produced. Next is the two-stage combustion, again to reduce the NOx emission. Next is a flue gas recirculation to use the inert nitrogen again and again to reduce the nitrous oxide or nitrogen dioxide of emission. And these NOx can be removed through any absorption method or adsorption method, or through selective or non-selective catalytic reduction methods. And next one is the carbon dioxide. One of the most efficient method for the removal of carbon dioxide is a chilled ammonia system. So this is the using of chilled ammonia to capture the carbon dioxide in it. So this is a trapping system. And next thing is air purifier. So in our household and other places, we have to maintain the air quality. So to improve the indoor air quality, we are using the air purifier. These can be active and passive purifiers. In the active purifiers, what happens? All the pollutants are collected and discharged into the air as a negatively charged particles. So this is not suggested. And in the passive purifiers, they are using the filters. So passive purifiers is a suggested method for purifying the air. And the most commonly used method for the purification of air or HEPA, which uses the high efficiency particulate air filters and ultraviolet germicidal irradiation UVGI. These are the most commonly used method to clean the air in the indoor. So now we have seen the brief about the week 5 lecture, which is air pollution control. Now we will discuss the sample questions for this week. So first question is identify the name of the equipment shown in the following figure. What is this equipment? What is this equipment? So in this equipment, the gases are coming inside, and here the gas is going outside. In between, what happens? It is passing through different trays. So the gas is passing through different trays. Finally, the clean gas is going out. The name of the instrument is forward settling chamber. And by introducing the number of trays in between the settling chamber, the efficiency of separation is improved. Okay. Next question is for Stokes law region, the terminal settling velocity is calculated as. So what is the formula? Calculate the terminal settling velocity based upon the Stokes law region. So the right answer is Pt is equal to GdP square into rho p minus rho g whole divided by 18 mu g. So g is acceleration due to gravity and dp is diameter of the particle. Rho corresponds to the density of the particle and the uh, carrier molecule, which is gas or liquid. And then 18 mu g again, g is the viscosity. Okay, so the right answer is Pt is equal to GdP square into rho p minus rho g whole divided by 18 into mu g. Next question is the efficiency of electrostatic precipitator ESP is. What is the formula? What is the right relation? So the right relation is 1 minus e power minus Vpm into AC divided by Q. So Vpm is the drift velocity, AC is the collector surface area, and Q is the volumetric gas flow rate. So efficiency is calculated using this formula. Typical air to cloth ratio in the fabric filter is in the range of. What is the typical air to cloth ratio in a fabric filter? The right answer is 1.5 to 3.5 meter per minute. So 1.5 to 3.5 meter is the typical air to cloth ratio in the fabric filter. Next is which of the following equipment is highly efficient with a removal efficiency of 0.99 percentage, sorry 99 percentage for the removal of particulate matter having size of 0.01 micron. What is the answer? Is it a gravity settler or ESP or fabric filter or cyclone separator? Okay. Right answer is the fabric filter. As we discussed earlier, the fabric filter is the highly efficient equipment, and it can remove the particulate matter of size greater than 0.01 micron. Rain lift is a process which is related to control of SO2 emission, control of NOx, or control of CO2 emission or particulate matter removal. The right answer is SO2 emission. So in this rain lift process, what is used as the medium? Activated carbon. So activated carbon is used as the medium to control the emission of SO2 emission. Next question is, which of the following is not a disadvantage of PET scrubbers? Relative high energy cost, problem of PET surge disposal, corrosion problems, indifference to the temperature and moisture content of gas. So, which is not a disadvantage they are asking. That means indifference to the temperature and moisture content of gas. This is not a disadvantage of PET scrubber. Next question is, with increase in particle size of particulate matter in air or gas, the removal efficiency of the cyclone separator. With increase in particle size, the removal efficiency will increase, decrease, or remains unchanged, insufficient information. So the right answer is increases. So the separation particle size should be greater than or equal to 0.2 times the top outlet diameter. That is the condition to increase the efficiency of separation in the cyclone separator. Okay. The next question is, calculate the plate area of an electrostatic precipitator ESP, removing the 85% of particulate matter from exit gas of a cement industry having 200 ppm of particulate matter. Assume the gas flow rate as 150 meter cube per second, drift velocity of particle as 0.11. So the drift velocity is given, flow rate is given, and the removal efficiency is also given. So the question asked is to find the plate area, collecting plate area, which is AC. So the right answer is 2587.0 meter square. So we have to use the formula eta is equal to eta is the collection efficiency, right? Eta is equal to 1 minus e power minus aw divided by q. So here a is the unknown one we have to find out, and w is the drift velocity which is given as 0.11, and q is the flow rate which is given as 150 meter cube per second. Right. We have to substitute all the known parameters here, and again a is calculated by 1 minus 0.85 is equal to e power minus aw by q. So again we have to eliminate this exponential factor, so we have to take ln over here. So ln of 0.15 is equal to, we have to substitute the value here, minus aw by q. Then you will arrive at the value of a. So ln of 0.15 will have some negative sign, so negative negative will cancel. Then you will find the a as 2586.98. So 2587 meter square is the right answer. And the next question is, in the previous question, what change is plate area of ESP would be required to improve the collection efficiency from 85 to 99? So already the question is telling that 85% is the efficiency. Okay. Now, to improve the efficiency from 85 to 99%, how much plate area is required? They are asking. So, and assume the exit gas flow as same. So, 150 meter cube per second, and W is also same. Just to improve the efficiency, how much area should be increased? They are asking. The right answer is 3689.78 meters square. So again, we will be using the same formula. Eta is equal to 1 minus e power w into a whole divided by q. Right. So here you have to substitute the efficiency as 99%, which is 0.99 instead of 0.85. And we have to find the area. So the area is 6279.77. They are asking what change is the plate area, how much the plate area should be increased to increase the efficiency they are asking. So previously the obtained plate area is 3689.78. Uh, 2587.0 meters square. So you have to subtract this 6279 obtained for 99% efficiency from the 85% efficiency calculated area. So you have to subtract A2 from A1 from A2, and you will obtain the value of 3689.78 meters square. So if you increase the area of the collector plate by 3689.78 meters square, the efficiency will get improved from 85% to 99%. This is how you have to calculate. So we have discussed the sample questions for assignment 5. Before going into the tutorial problem, do you have any doubts? Any doubt in the sample questions? Okay. We'll move into the tutorial questions. We will solve some similar problems. Okay. So the first problem is, since we have seen the electrostatic precipitated based problems, we will solve some similar kind of problem. Calculate the plate area of an electrostatic precipitator ESP, removing 90% of the particulate matters PM from the exit gas of a cement industry having 200 ppm of particulate matter. What change in plate area of above mentioned ESP would be required to improve the collection efficiency from 90 to 99%? So it is a similar kind of problem. You have to assume the exit gas flow rate as 150 meter cube per second, and the drift velocity of the particle is 0.11. Okay, so the formula is, we know eta is equal to, same formula is applied. Okay, eta is equal to 1 minus e power minus w into a divided by q. So we need to find the area for 90% as well as 99%, and we have to subtract them. Find the increase in A. So 1 minus, I will write it directly, ln of 1 minus eta is equal to minus w into A by q. Okay, first you need to substitute eta as 0.9 for the 90%. Okay, in the next problem, calculate the area 2. We have to substitute the eta again as 0.9. 9. Okay. And this side will not change. And drift velocity and Q is same for both the 90% and 99%. So W is 0.11 and Q is 150 meter cube per second. Okay. So if you substitute this, A1 will be obtained as 3139 0.89 meter square, and A2 will be obtained as 6279.77. Right. So if you subtract A2 from A1, you will obtain 3139.88. So only you have to calculate the area of 90% efficiency and the area of 99% efficiency. How much the area should be improved is the question. So in this way, you can obtain the increase in plate area. And next is also a similar type of question with small modification. An ESP is to be constructed to remove the fly ash particles from stacked gases flowing at the flow rate of 10 meter cube per second. So the flow rate is 10 meter cube per second. Analysis of a similar system shows that drift velocity can be taken as W is equal to 3.0 into 10 to the power minus 1 into dp. Instead of giving the direct value of W, drift velocity is W, instead of giving the direct value, they have mentioned like W is equal to 3.0 into 10 power minus 1 into dp. So here dp is the diameter of the particle and the unit of the drift velocity is mentioned as meter per second in the question. So directly if you substitute the value of dp, you will obtain the W in meter per second. This is what mentioned in the question. Determine the plate area. So again the question here is to calculate the collector plate area required to collect the particulate matter of 0.5 micron size with 99% efficiency. So efficiency is given and W is given. You have to multiply it with diameter of the particle. Substitute the 0.5 here, okay, to calculate W. And then flow rate is also given. So this is Q. Again, you have to use the same ESP efficiency formula. You have to use the same formula. Theta is equal to 1 minus e power minus W A divided by Q. So we have to take ln on one side to cancel the exponential. Finally, you will arrive at the area of 307.011 meters. So one formula will be used to solve all these similar kind of problems. So next question is a MSW, which is a municipal solid waste power plant, is emitting 45,000 meter cube per hour flue gas. So the flow rate of the gas is given. It is proposed to install an ESP with a collection efficiency of 96.8%. So efficiency is given as 96.8. Calculate the total area of collection electrodes if the collection efficiency is 99.5%. So we have to calculate the area for 99.5% also and 96.8% also. How much additional collection electrode area would be needed? A2 minus A1 is to be calculated. Drift velocity of the particle has been determined experimentally as 0.13 meter per second. So W is directly given and Q is mentioned as 45,000 meter cube per hour. Since the unit of W is meter per second, we have to convert this 45,000 meter cube per hour into meter cube per second by substituting 3,600 here in the denominator. So now the Q obtained is 12.5 meter cube per second. This is to be substituted in our efficiency formula. So eta is equal to 1 minus e power minus Vpm. So this Vpm is the drift velocity, which is nothing but W, which is given as 0.13 meter per second. AC is to be formed and Q is, now the new Q is 12.5 meter cube per second. Okay. For first case, it is given as 96.8. So we have to substitute 0.968. So the area obtained is 330.96. Again, for the second case, we have to substitute 99.5% efficiency, which is nothing but 0.995 is equal to 1 minus e power minus 0.13 into area whole divided by your mu q obtained is 12.5. So now the A2 is, this is the A1, and the A2 obtained is 509.45. So the additional area required is calculated by subtracting A1 from A2. So A2 minus A1 is 509.45 minus 330.96, which is nothing but 178.49. So this is the additional collection electrode area required to improve the efficiency from 96.8 percentage to 99.5 percentage. Okay. One similar problem is here. The question is given. Please try to solve this one. We will discuss the answer. So the question here is MSW based power plant is emitting 55,000 meter cube flue gas area. So now the Q given in this question is 55,000 meter cube. It is proposed to install an ESP with collection efficiency of 96.8 percentage. Calculate the total area of the collection electrode. So AC is asked, eta is given as 96.8. Drift velocity of the particle has been determined experimentally as 0.13 meter per second. So W is given, Q is given, eta is given, only AC is asked. Okay. Use the formula eta is equal to 1 minus e power minus W into AC whole divided by Q. Solve this one and tell the answer. Simple question. Before substituting Q value, we have to again convert the meter cube per hour to meter cube per second. For that, we have to divide the value with 3600. We know, right? 1 hour is equal to 60 minutes. Again, 1 minute is equal to 60 seconds. So 60 into 60 seconds. That's why we are dividing it with 3600. What is the total area of the collection electrode? Has anyone solved this question? Let's see the answer. So the right answer is 404.3 meters square. So efficiency is equal to 1 minus exponential of minus BPM into AC divided by Q. So drift velocity is 0.13, AC is unknown, Q is obtained by substituting 55,000 divided by 3,600, and the ln of 1 minus 0.968 is taken to eliminate the exponential factor. So we have to solve this value to arrive at the answer. which is 404.3 meter square. This is the area of collecting plate required to achieve the efficiency of 96.8% using the electrostatic precipitate. Okay. Do you have any doubt in this electrostatic precipitator problem? Next, we will move on to other problems. Okay. Now, the next problem is calculate the sedimentation rate in the gravity separation for the particle size limiting diameter is given as 7 micron. The particle density is given as 1040 kg per meter cube, and the liquid density is given as 1000 kg per meter cube, and the viscosity of continuous phase is given as 1 into 10 power minus 3 Newton second per meter square. So for the gravity-based separation, laminar gravitational free settling velocity, the formula is, so we have to note down this formula. Okay, so the formula is Ug is equal to dp square into rho s minus rho l into g divided by 18 mu. So dp is the diameter of the particle, which is given as 7 micron. So 7 micron, you have to convert everything to meter. Okay, so micrometer, so 10 power minus 6 meter it is. Okay, dp square, so 7 into 10 power minus 6 the whole square, and rho s is the solid particle density. So the particle density is mentioned as 1040. So 1040 minus the liquid density rho L is given as 1000. So 1040 minus 1000 into G value is constant 9.81 divided by 18 into mu. So mu here is the viscosity. So viscosity is 10 power minus 3, which is nothing but 0.001, and it is substituted here. Okay, so if you solve this one, you will obtain Ug as 1.068 into 10 power minus 6 meter per second. Okay, this is the sedimentation rate in the gravity separation for the particle size of 7 micron. Okay, the only thing is you have to note down this formula. Ug is equal to dp square rho s minus rho l into g divided by 18 mu. All the data are given. I have to substitute it to find the Ug. And next question is a multi-tray settling chamber having 8 trays. So note down 8 trays are there, including the bottom surface. Handles 6 meter cube per second of air at 20 degrees Celsius. So the first data given is the flow rate. 6 meter cube per second is the flow rate of the air. The trays are spaced 0.25 meter apart. So the spacing, which is the delta H, is given, and the chamber is to be 1 meter wide. So W is equal to 1 and 4 meter long. L is equal to 4. What is the minimum particle size of density? 2000 kg per meter cube. So this is the density that can be collected with 100% efficiency. They are asking you the particle size, and assume the particle of the particular size is having the density of 2000 kg per meter cube, and the collection efficiency should be 100%. What will be the efficiency of the settling chamber if 50 micron particles are to be removed? Laminar flow condition within the chamber and the presence of no dust initially on the trays may be assumed. In the above example, if the laminar assumption is justified. Initially, they are asking you to solve this problem by assuming the laminar flow condition. Okay, and they are asking you whether this laminar assumption is justified or not, whether it is laminar or turbulent. They are asking. Then, if it is not laminar, what is the collection efficiency for 56 micron and 50 micron particles? So this is the question. I will write it once again. A multi-tray settling chamber having 8 trays, including the the bottom surface handles the 6 meter cube per second of air at 20 degrees Celsius. The trays are spaced 0.25 meter apart and the chamber is to be 1 meter wide and 4 meter long. What is the minimum particle size of density 2000 kg per meter cube that can be collected with 100% efficiency? What will be the efficiency of the settling chamber if 50 micron particles are to be removed? First, they are telling the particle size is to be found for 100% efficiency. And for 50 micron particles, what will be the efficiency they are asking? Laminar flow condition within the chamber and presence of no dust initially on the trains may be assumed. Using the laminar assumption, we are going to find these two answers. And to solve this one, we should know the formula of the diameter of minimum diameter of the particle. We are going to use this formula, which is square root of 18 mu g into q divided by n into w into L into g into rho p minus rho g. Okay. Then the next set, this is the first part, and the second part is in the above example, is the laminar assumption justified? Whether it is truly laminar or not, we have to check it. If it is not laminar, what is the collection efficiency? Again, we are going to calculate the eta for 56 micron particles as well as the 50 micron particles. Okay. So now to obtain the value of Tp, which is the minimum diameter of the particle using this formula, what are the parameters required? So Tp minimum is equal to square root of 18 mu g into q. Mu g is the viscosity, right? So the viscosity is given as, okay, viscosity is not given here. So, but the temperature is given. So at 20 degrees Celsius, they have mentioned. So mu g at 20 degrees Celsius is 1.81 into 10 power minus 5 kg per meter second. Okay. Next is the Q. Q is the flow rate. Flow rate is given in the question as 6 meter cube per second. So it is also substituted. And N is the number of trays. So number of trays is 8. So N equal to 8 is substituted here. And W. So W is the width. So width is 1 meter wide. So W is substituted. And L is length. It is 4 meter long. So the chamber is 1 meter wide and 4 meter long. So L is 4. And G is constant, which is 9.81. Rho P minus rho G is here. And here the particle density is given as 2000 kg per meter cube. So the rho g is generally, if it is liquid means it will be 1000 kg per meter cube. So here anyway the particles size density is very much higher. So what they are telling is to eliminate the rho g. So only rho p is here, which is 2000 kg per meter cube. So if we solve this one, we will obtain the minimum particle diameter as 56 micron. Okay. So once the dp is found, okay, once the dp is found, we have to calculate the efficiency. So now we have found for 100% efficiency, what is the minimum particle size? So the minimum particle size is 56 micron. Okay, now they are asking what would be the efficiency of settling chamber if 50 micron particles are to be removed. Actually, 100% efficiency can be achieved when the particle is of size 56 micron. Now we are using the 56 micron particle only. So to calculate this, we should take this formula, which is nothing but efficiency is equal to dp, diameter of the particle, divided by minimum diameter of the particle whole square. So now the diameter of the particle mentioned in our question is 50 micron. Okay, so dp is 50. So we should not confuse with this one. dp is 50. dp minimum is calculated one, which is 56 micron. Okay, so 50 divided by 56, the whole square is 80%. So the efficiency of dp is equal to 80%. So first part is solved now. What they are asking is, in the second part is, in the above example, is a laminar assumption justified or not? If not, what is the actual collection efficiency for this 56 and 50 micron particles they are asking? So to find whether the particle Reynolds number, whether it is a laminar assumption is right or not, we should use the particle Reynolds number. So if the Reynolds number is greater than 1000, then it is coming under the turbulent. Okay. So if it is greater than 1000, in this case, it is coming under the turbulent regime. So now we are going to calculate the particle Reynolds number using the formula RE is equal to dP into rho g into Vt mu g. To calculate Vt, we don't have enough data. So what we are using here is Vt is calculated with the help of flow rate and length and width. Okay, so the flow rate is given as 6 meter cube per second. 6 meter cube per second, and the length is given as 4 meter into the width is given as 1 meter. Okay. So meter square and meter cube will get cancelled. You will arrive at meter per second. Here the Vt is calculated in this way. So for the particle of size 56 micron and for the particle of 50 micron, we have to substitute the diameter of the particle here, and all the other parameters are same. So this is how the Reynolds number is calculated. This is 9281 and this is 8287. Both are in the turbulent regime. So the question asks is the laminar assumption justified? So it is no. So the laminar assumptions are not correct for both the cases. We know that it is in the turbulent regime. So to calculate the efficiency in the turbulent regime, the formula is efficiency is equal to, so the turbulent efficiency is equal to 1 minus exponential of minus the laminar efficiency. We now know the efficiency of the particle when we have assumed the laminar flow condition, right? So it is 80 percentage for 80 percentage for 50 micron particles, and it is 100 percentage for 56 micron particle, right? So we now know that for both the cases we have to calculate. So if it is 50, the efficiency is 80 percentage. If it is 56, the efficiency is 100 percentage. So that is what we are substituting in this formula. So turbulence efficiency is equal to 1 minus exponential of minus 1. So 1 is 100 percentage for 56 micron particle. So the answer is 63 percentage. Then for the 50 micron particle, the efficiency is 80 percentage. It is already calculated. So efficiency is actual efficiency is equal to 1 minus exponential of minus 0.8, which is 55 percentage. Now we have calculated the actual efficiency for the particle size of 56 micron and 50 micron. Okay. Do you have any doubt in this problem? Initially, they are asking the size of the particle. If we are assuming the 100% efficiency, then they are giving you one particular size of the particle and asking you to find what is the efficiency. That can be obtained by using the formula efficiency dP is equal to dP divided by minimum dP. Okay, this minimum dP is obtained with the formula square root of 18 mu g q divided by NWLG into rho p minus rho g. Okay, so the first part is solved. The second part is whether the laminar assumption is justified or not, they are asking. So to check whether the laminar condition is prevailing or not, we are going to determine the particle Reynolds number, which is RA is equal to dP rho g Vt divided by mu g. So with this one, we are determining whether the laminar flow conditions are there or turbulence conditions are there. Next, if not, what is the collection efficiency? If not means they are asking the turbulence collection efficiency, which is obtained by using this formula. Eta turbulence is equal to 1 minus exponential of minus eta lambda. Okay, I hope I hope this is clear. We can move to the next problem. Can we? So now the next question is calculate the net air to cloth ratio. So just to calculate the air to cloth ratio for a reverse air bag house with 10 compartments containing 276 bags each. The diameter of each bag is 11-inch and the bag height is 28 feet. One of the compartments is always offline for cleaning and another is offline for maintenance. Use a gas flow rate of 350,000 ACFM. So ACFM given here is the actual cubic feet per minute. So this is a bag filter. So it is very simple. So it has many compartments like this. So there are 10 compartments and it is having many bags like this. So the number of bags are 276. Okay. They are asking the air to cloth ratio and the diameter of the bag. So this diameter of the bag is 11 inches and the height of the bag is given as 28 feet. So we need to convert all the unit to single unit before using it. The gas flow rate. So gas is flowing in and flowing out of this bag filter. Gas flow rate is 350,000 ACF. Okay, since it is in feet, we have to convert everything into feet. Okay, so individual area of the bag is first calculated. So to calculate the individual area of bag, the formula is pi into d into h. Okay, so pi is constant. D is the diameter. Diameter is 11 inches. We to convert inch to feet. Okay, so we are dividing it with 12 feet. Okay. Hmm. 1 feet is equal to 12 inch. So 11 divided by 12 feet into h. Height of the bag is 28 feet. So if you multiply this, you will obtain the individual area as 80.6 feet square per bag. This is for a single bag. Okay. Now the total bag area. So for 276 bag having of 10 compartments, we have to calculate the total area. To calculate the total area, so we have to multiply the individual area with number of bags per compartment into number of compartment, which is 80.6 into 276 into 10, which is 222,456 feet square. Okay, this is the total area. Since we know the total area, now we can easily calculate the air to cloth ratio. So air is the air to cloth ratio is obtained by Q divided by A. So this is the formula Q divided by A. Q is already given. Given as 350,000 feet cube per minute. Okay. Now to calculate the area only, you are calculating the individual area of the bag into number of bags and number of compartment in each bag. So it is 222,456 feet square. If we divide this one, you will obtain the net air to cloth ratio as 1.57 feet per minute. So this is the answer. Okay. Next question is estimate the liquid purge rate for a scrubber system treating a gas stream of 25,000 SCFM with a particulate matter of loading 1 grains per SCF. So amount of grain per SCF is 1 grain. Assume the scrubber particulate matter removal efficiency. Eta is given as 97% and the maximum suspended solid level desirable in the scrubber is 3%. So this is the solid fraction present in the scrubber. This 3% is by weight. Okay, and unit conversion factor is also given. To convert the pounds to grain, 1 lb is equal to 7,000 grain. Okay. The question is to calculate the flow rate, which is the liquid purge rate. With the given data, how we can calculate the liquid purge rate? First, the liquid purge stream flow rate is equal to, the formula is to calculate this, the purge stream flow rate is equal to total mass flow rate divided by purge stream density. Okay. To calculate this, the purge stream density is calculated by purge stream density is equal to density of water into specific gravity. Okay, so density of water and specific gravity, all these are standard ones. So we know the purge stream density first. Only unknown thing is to calculate the total mass flow rate. To obtain this mass flow rate only, we are going for this formula. Total particulate matter is equal to gas flow rate into particulate matter loading. So this will give you the inlet mass. What is the inlet particulate matter weight? Okay, which is equal to gas flow rate Q. It is given in the question, which is 25,000 feet cube per minute, and the particulate matter loading. So at this rate, how much grains are there per feet cube? They are telling means 1 grain is there. So you have to multiply this. So you are converting the grains to LB, which is 1 LB divided by 7,000 grain. So now the inlet mass, amount of particulate matter which is going in inside that chamber is 3.57 pound per minute. Okay, now we know the inlet mass. Now to find the collected mass, this is the inlet mass going through the scrubber, which is 3.57. But what is actually collected here is the scrubber efficiency. So this scrubber efficiency is given as 97%, right? So the efficiency is 97%. What is coming out, what is collected mass is 3.46. So how this is calculated means 0.97 efficiency into the inlet mass 3.57, we can obtain the collected mass, okay, which is 3.46 lb per minute. Now we are going to find the mass, which is the amount of solids in this purge stream, which is 3.46 lb per minute, or 3% of the total purge stream. So that is the condition mentioned in the question. Maximum suspended solid level desirable in the scrubber is only 3%. So we have to calculate the total weight. To calculate the total weight, the formula used is concentration of solid is equal to particulate matter removed into 100 whole divided by W. Okay, we are going to find this W only. So this W is the amount of the weight of the the total mass flow rate is calculated here. In this flow rate is calculated in terms of weight with the help of this equation. We know the concentration percentage allowed is 3% and the particulate matter removed is 3.46, right? So using this formula, we are calculating the purge stream mass flow rate, which is 3.46 divided by 0.03 is equal to 11.53 lb per minute. So this is the mass flow rate. Like it is this much pounds, right? So in terms of mass, this flow rate is determined. Now we are going to calculate the purge stream flow rate by dividing this mass flow rate with purge stream density. So density is calculated as said earlier, density of water into specific gravity. So these are all standard values, which is 8.34 into 1.03, so which is 8.59. So we have to divide the total mass flow rate with this purge stream density to obtain the purge stream flow rate. This is the liquid flow rate, which is 13.4 gallons per minute. Okay, this is how the liquid purge rate is calculated from the given data. First, the aim is to calculate the liquid purge rate. So the formula is liquid purge rate is equal to total mass flow rate divided by the purge stream density. To calculate the mass flow rate, initially you should know how much amount of solid is there. For that, you have to calculate the inlet mass of the particulate matter and outlet mass of the particulate matter. And with the help of the relation given as 3% is allowed in the scrubber, we are calculating the mass flow rate. Okay, then you are getting the liquid flow rate value. And coming to the next question, a venture scrubber is used to collect the PM particulate matter from a gas stream. The liquid flow rate through a scrubber is 20 gallon per minute. So here directly the liquid flow rate is given, which is 20 gallon per minute per 1000 cubic feet per minute of gas. And the relative velocity, so the relative velocity VR is given as 400 feet per second. The gas is air. So the gas used is the air at standard temperature pressure conditions and carries the particles of density 1500 kg per meter cube. Determine the efficiency of the scrubber as a function of particle diameter. So the question is to calculate the efficiency of a scrubber as a function of diameter of the particle. So this is the question asked. Consider the viscosity of the gas as a 1.8 into 10 power minus 5 kg per meter second. And the empirical factor for throat geometry and other parameters, K is 0.2. So this is the data given. So to determine the collection efficiency in the venture scrubber, this is the formula. So efficiency of venture scrubber is equal to 1 minus exponential of minus KL into square root of psi. So K is given as 0.2. K is nothing but the empirical factor, which is already given in your question. Next is the L. L is the liquid flow rate. It is also given. So L is equal to 20 gallon per minute per 1000 cubic feet per minute of gas. And then psi. So psi is the unknown factor here, which is the impaction parameter. It is obtained by using this formula, C into rho P into dP square into VR divided by 18 mu G into T naught. Okay, here C is the Cunningham correlation factor. You can leave this factor and keep it as C itself. And then rho is the density of the particle, which is already given. So rho P is 1500 kg per meter cube, right? VR is the relative velocity. It is given as 400 feet per second. And mu g is already given. The viscosity of gas, mu g is equal to 1.8 into 10 power minus 5 kg per meter second. And d naught is the diameter of the particle. Here diameter is not given. If it is not given, you have to calculate this diameter with the help of this formula. D naught is equal to 16,400 whole divided by VR, which is relative velocity already given, plus 1.45 into L power 1.5. L is the liquid flow, that is also already given. You have to calculate D naught and substitute the D naught in this equation to arrive at the value of psi, and then you have to substitute the value of psi here to arrive at the value of efficiency of this venture scrubber. Okay, this is how you will be solving this problem. So now coming to the solution, as I said, the collection efficiency is calculated using eta is equal to 1 minus exponential of minus KL into square root of psi, and impaction parameter formula is given here. Droplet diameter is calculated by using this formula. So we are substituting the values now. D naught is equal to 16,400 divided by VR, which is 400. Next, plus 1.45 the L power 1.5. So L is 20 gallon per minute, so 20 power 1.5. So now we know the value of D naught. So D naught is equal to 170.7 micron, which is written as 171 into 10 power minus 6 meter. Okay, 171 into 10 power minus 6 meter. Now VR is given as 400 feet per second. Since all the units should be same, we are converting the feet per second into meter per second. And then the new VR value is 122 meter per second. 1 feet per second is equal to 0.3048 meter per second. Using this conversion, we are calculating the VR. So now, once D naught is found, we need to calculate the psi. Okay, so psi is equal to C. C is unknown, so we can keep it as C itself. Okay, and rho P is already given 1500, and dP square. Now the dP is the unknown. We have to calculate the efficiency as a function of dP only. That is the question asked. So we have to keep dP as dP itself into 122, which is the VR. So now VR is also substituted. Whole divided by 18 mu g. Mu g is 1.8 into 10 power minus 5. It is substituted. And D naught is just now calculated as 171 into 10 power minus 6. So now we have obtained the psi value, right? So psi is equal to 3.3 C into dP square. Just substitute this psi value in this efficiency equation. So now the efficiency is equal to 1 minus exponential of minus k. So the k value is given as 0.2, right? 1 minus exponential of minus k into 20 gallon per minute per 1000 cubic feet per meter of gas. So this is the liquid flow rate. 20 is already given. This is L. Okay. Into square root of psi. So the square root is written as power half here. So the psi value obtained is 3.3 C into dP square, right? So this square and square, 1 by 2 and square will get cancelled. So dP will be there and C power half will be there. And if we solve these terms, you'll obtain minus 7.27. So the final answer is, this is the efficiency of the scrubber. Eta is equal to 1 minus exponential of minus 7.27 C power 0.5 into dP. So the question is to determine the efficiency of scrubber as a function of particle diameter. So function of particle diameter is nothing but dP. So now we have obtained the equation of efficiency in terms of dP. Okay. Next question is, a packed filter handling 1 meter per second of standard air is packed with fibers of size 100 micron. So packed filter is going to handle the velocity of 1 meter per second air, which is of size, it is packed with the size of fibers 100 micron in diameter. Dust laden air passes through the filter with velocity. So velocity of dust laden air is 1.5 meter per second, and the packaging density is now the 0.1. Okay. The average diameter of the particle in the air. This is the diameter of the particle, which is 1 micron, and the individual fiber efficiency is given as 0.6. So with all these parameters, the question is to determine the dimensions of a packed filter if overall efficiency eta is given as 99.5%. And the one assumption is given, like width is equal to height. What is the filter length if efficiency? Again, L is asked. So filter length is asked if efficiency is increased to 99.9%. Okay. All the data are given, so we have to substitute them directly in the formula. Okay, so first is to determine the dimensions of the packed filter. So to determine the dimension of the packed filter, to determine W, H, and L, that is the question. We need to determine W, H, and L. And in the question it is mentioned W and H are same. So we need to calculate only two values. So to calculate the W is equal to H is equal to square root of AF. So this is obtained with H is equal to square root of AF. The formula to calculate AF is, which is phase area is equal to Q divided by B into 1 minus F. The flow rate is given as 1 meter per second, right? So 1 is substituted here, and the V velocity is 1.5 meter per second into 1 minus FF is given as 0.1, which is the packaging density. So if we are substituting all the values, we will obtain which is sorry, rho f is given as packaging density is given as 0.1. So AF is equal to 0.74 meter square. So H is equal to AF power half, which is square root of 0.74 is 0.8 is 86 meter. Now WH is determined. Then to calculate the length of the filter, L is equal to pi df into 1 minus 4 divided by eta f into 4 into rho f. So to calculate this one, we need to substitute all the values. Again, all the values are given. So the value of rho f is 0.1 and the df diameter is already mentioned as 1 micron, right? So, size of the particle is 100 micron and packaging diameter, okay, which is 100 micron. Then eta efficiency is here individual fiber efficiency is given as 0.6 and again 0.1 is substituted here into ln of 1 minus efficiency. So this efficiency corresponds to the efficiency of the whole process. So the overall efficiency is 99.5. This efficiency is different from this one. Okay, it is the individual fiber efficiency, and this is the overall efficiency. Once you substitute all the data, you will obtain L as L is equal to 0.006236 meter. And the second question is find the filter length L if the efficiency is increased to 99.9. So all the other terms will be same for the part B also. Only we have to change the efficiency, which is overall efficiency is now changed to 99.9 percentage. So we are substituting 0.999 here. So now the length obtained is L is equal to 0.01084 meter. Okay, this is how you should be calculating the dimensions of the packed filter. So if it is a packed filter, to calculate the dimension, they are telling us you need to calculate the width, height, and the length of the packed filter. And if W is equal to H, we can calculate W from H itself. So general formula for H is equal to square root of phase area. Phase area is obtained using this formula, and length is obtained using the standard formula. So all the data are given. We need to just substitute the values to obtain the dimensions. Okay. Do you have any doubts so far? Shall we proceed? So now the next problem is, what is the aspect ratio for a 5-field? So here 5-field there. For a 5-field electrostatic precipitator having the collection plate height. So the height of the plate is given as H is equal to 30 feet and the length of the plate L is given as 9 feet and the width of the plate W is given as 50 feet. They are asking the aspect ratio. So the general formula to calculate the aspect ratio in the ESP is, you have to note it down, it is length divided by height. So length is 9 feet, height is 30 feet, and they have mentioned 5 fields are there. So you have to just multiply this with 5 fields. So the right answer is 1.5. So the aspect ratio for a 5-field electrostatic precipitator is 1.5. Okay. And coming to the last problem of today's session, calculate the overall collector efficiency of gravity cyclone for the dust sample data given in the following table. What is the right answer? So I have already told you, like total efficiency is calculated with the help of the fractional efficiency, which is the summation of Wi. Right. So this is the weight fraction. This weight fraction is obtained by dividing the individual mass with the total mass. So I have to add all the weight fractions, and you have to multiply it with the respective fractional efficiency to arrive at the total collector efficiency. So this is the general formula. Okay. Since we have discussed the same model problem, can you please try it? It's very simple. Total efficiency is equal to first. So the first one is the total mass, capital M, is equal to 100. And the fractional for each fractional size, the respective weight is given and the fractional efficiency is given. So to calculate this, first one is calculated as 2 by 100 into the Wi is the Mi divided by capital M. So the individual particle mass is 2 gram. So it is written as 2 here, divided by the total mass. So the total mass of all the particle is 100 gram. So 2 divided by 100 into the individual fractional efficiency. So individual fractional efficiency for a particle size less than 5 micron is 1%. So into 1. Okay. Plus the next term is 3. So for 5 to 10 micron particle, the individual mass is 3 gram. So 3 divided by 100 into, and its respective fractional efficiency is 7. Okay. Like this, you have to calculate for all the fractions and you have to add them. Okay. Finally, you have to calculate for particles of size greater than 70 micron, which is given by 5. They are all together about 5 grams, okay, out of 100 grams. So 5 divided by 100 into, and its respective fractional efficiency is 100. So we have to multiply the weight fraction into the fractional efficiency, and the summation of the weight fraction into fractional efficiency for all the particle size will give you the total collector efficiency. Okay. So the right answer is 80.9%. As I said, it is calculated by summation of all weight fraction into individual efficiency. Do you have any doubts so far? Thank you all. So now I will quickly go through the different kind of problems of this week. What are the important formulas? Most of the problems are based on the electrostatic precipitator. So the general formula is efficiency is equal to 1 minus e power minus W into A by Q. W is drift velocity, A is the collector area, and Q is the gas flow rate. If one parameter is given and the other parameter is unknown, you have to calculate the unknown parameter using this formula. Okay. Similarly, when the efficiency is when the efficiency is increased to 85 to 99%, like this they are telling you, and what should be the increase in the plate area mix? We have to calculate the area for each efficiency, and you have to subtract A2 minus A1 and find the increase in the plate area. Okay. This is also same kind of problem. And in this one, only difference is instead of giving the drift velocity directly, they have mentioned like W is equal to 3 into 10 power minus 1 into dp. So dp value is also given. So you have to find the drift velocity. All other parameters are same. And sometimes they will give you the gas flow rate in different unit, which is meter cube per hour. So you have to calculate the gas flow rate from meter cube per hour to meter cube per second, and you can use the same formula. Efficiency is equal to 1 minus e power minus WA divided by Q to calculate either efficiency or the collector area. Okay. Next is the sedimentation rate calculation. This is for gravity settling. So by using UG formula, which is UG is equal to dp square into rho s minus rho l into g divided by 18 mu, you can calculate the sedimentation rate. So this is for gravity settlers. Next is again for the gravity settling chamber with different trays. They are asking you to find the diameter of the particle, and for the given diameter of the particle, they are asking you to find the efficiency. Okay, and if they are asking you to check whether the condition is laminar or not, we are going to use the formula particle Reynolds number. And if it is laminar, then you can leave it as it is. Like you can say for 50 micron particles, the efficiency is 80%, and for the dp minimum 56 micron particle, the efficiency is 100%. You can leave the problem as it is. If it is not laminar condition, if the RE is exceeding 1000, then if it is in turbulent condition, you have to convert the laminar efficiency to turbulent efficiency by using this formula. Efficiency, turbulent efficiency is equal to 1 minus exponential of minus laminar efficiency. Okay. And next question is to find the air to cloth ratio. This is a back filter kind of problem. The formula is Q divided by A. Flow rate is given, area is to be determined. To determine the area, you should also take into account of how many number of bags are there and how many compartments are there in each bag. So all these things you have to include to calculate the total bag area. The formula is very simple. To calculate the net air to cloth ratio, the formula is Q divided by area. Only thing is you have to calculate the area carefully. And next one is to calculate the liquid purge rate. So to calculate the liquid purge rate, here they have given the weight fractions. So the formula is to calculate the mass flow rate and divide it with the density to calculate the liquid flow rate. To arrive at the mass flow rate, initially you are calculating how much amount of solids are there in the stream, purge stream, and we are calculating the mass flow rate. Okay. Next is the scrubber. For the scrubber based problems, depending upon the scrubber, you have to select the formula. If it is the Venture scrubber, you have to choose this formula. Collection efficiency of scrubber is equal to 1 minus exponential of minus KL into square root of psi. Using the psi formula and D naught formula, you calculate all the parameters, and you need to express the efficiency in terms of diameter of the particles. Okay. And next is a packed filter based problem. So in this one also, to calculate the dimension WHL, we have the standard formulas. We have to substitute the data given in the correct unit to arrive at WH and L, which is the dimension of the filter. Next is the aspect ratio. So aspect ratio of the back filter is Q by A, and here the aspect ratio of the electrostatic precipitator is L by H. Okay. And there you will be calculating the area with the help of how many bags and how many compartments. Here you have to note down how many fields are there since it is electrostatic precipitator. So here 5 field is used, so you have to multiply the value of L divided by H with 5 field to arrive at the aspect ratio. And finally, we have seen the gravity settling efficiency. So the total efficiency is calculated with the help of individual fractional efficiency. So the formula is sum of all weight fraction into individual fractional efficiency. So this is a formula to calculate the total collector efficiency. Thank you. If you have any doubts, You can ask. Ma'am, whether all the formulas will be given in the final exam also. It's very difficult to remember these formulas. Simple formulas, I think they will not be given. But if you see in this question, the DP formula itself mentioned in the question itself. Okay, like this, maybe the difficult formulas will be given. Okay, okay. If you have any doubts, you can stay online, or else you can leave. Thank you for joining today's session. I will be handling the next live session on next Saturday, 3 to 5 p.m. using the same Gmeet link. And this recorded video will be uploaded in the YouTube and presentation will be uploaded in the Drive link. You can refer it later also. Thank you.